In this class, we're going to consider the notation that we use for integration. So in general, calculus is fairly notation heavy. There's quite a lot of notation to figure out. And if you've already done Calculus 1, which I assume you have, then you've already seen some of the notation challenges that we face there. I would say that in Calculus 2, in integration, there's probably more of a challenge with the notation, but all students have to go through that pain and you'll get used to it fairly quickly. There's a couple of things that make it maybe slightly more challenging, and we'll chat about those as we go through this class. So the first thing is, how do we notate an integral? Like, how do we say that we've got an integral or found an integral, or what is the equivalent basically of in differential calculus, in Calculus 1, in differentiation, what is the equivalent of like the f prime of x, or the dy dx. So these are the kind of equivalent notations we want to build up here in integration. Well, it all comes down to this symbol here called the integral sign, and you can think of the integral sign, which is kind of like an elongated S shape, I guess, really. Different students have got different ideas of what it looks like, but yeah, kind of an elongated S. That's a popular way to visualize it. This symbol here is actually based upon, or one of the interpretations of it, which we'll see later in the course as we explore this idea, is based upon a sigma. And if you take a sigma and you kind of elongate it in some way, you can end up with this symbol. That's one interpretation, and you'll see later on why it's related to a sigma. Remember, a sigma is a symbol that we use to represent adding things together, and we're going to combine that with the idea of a limit, which we looked at in Calculus 1, to basically define later on this thing that we call the integral. But for the time being, really the idea is just to get the notation down. So we're just dealing with this here to represent the integral. So if, for example, we take the integral, let's say we take the integral of some just generic function f of x. The other thing that we have to add in integration is this dx on the end. Now this can be quite confusing at first. We read the dx as with respect to x, so let me just write that up. So the dx we should think of in our heads or say out loud as with respect to x. It doesn't have to be x, it can be any variable. Part of the reason that we need this, this function here, we don't know what it is in this case, it's some f of x function. It's not always just an f of x function. I mean, as you move forward, maybe not in this course, but in future courses, you're going to see functions which are defined not only on one variable, but maybe on two or even more variables. When you've got a multivariable function, you need to know which of the variables you're integrating with respect to. In other words, if you had, for example, f of x and y function, which has got x's and y's in it, if you were integrating dx, so with respect to x, you would treat the x as your variable, so you would apply the integral rules to the x, but you would treat the y terms as a constant term and treat them basically like a number. So we need to know when we're integrating what we're integrating with respect to. There's not that many scenarios in this course really where it becomes a problem. It's just a notational thing at this point. Every time you've got an integral sign, and this is a really important point, every time you've got an integral sign, you've also got to have a dx, or whatever the letter is. Usually it's going to be an x, because usually we're dealing with an f of x function, but those two have to go together. You cannot have this without this. It wouldn't make any sense. So just be ultra careful with that sort of relationship between those two. But we defined in the previous class the integral as being the antiderivative. So we can say that this thing here, the integral of f of x with respect to x, is equal to uppercase f of x. In other words, it's equal to the antiderivative of the function f of x. Okay? So that's how you would read this. So the integral of f of x with respect to x is equal to the antiderivative of the function f of x. So we're still not quite at the point in this course yet where we're going to learn the rules for integrating. We're going to start that eventually in the next class. We've got to build up all these notational and foundational ideas like antiderivatives first. But I've just got a couple of examples here we're going to run through just to show how you would start to think about that process. So This here says integral with respect, the integral of 4x squared with respect to x. We want to learn eventually how to evaluate that. The thing that we find is going to be the antiderivative of this function. Now, you're going to learn in the next class how to actually go about this, but I'm just going to show you how this one would work. So this one comes out to be 4 over 3 x cubed. And then remember in the previous class, or maybe even 2 classes ago, we said that when you find an antiderivative, you can put a constant on the end, which we just notate as a plus c, because if you differentiate a constant, in other words a number, then you get 0. So basically differentiating this whole thing here, including the plus c, would give you this here, 4x squared, regardless of what the c value is. In other words, there's infinitely many antiderivatives of this function, and that infinite variety of functions, antiderivatives, is kind of notated by the c. The c can be any arbitrary value that you need. Later on, we're going to do things, learn techniques where we've got to find the c value, and that's a different story, and we'll deal with that at the time. But for the time being, we're basically saying that if you saw this here, this should tell you to integrate. Now, I've done this here by a technique that you've not yet learned. We're going to learn that, the power rule, in the next class. But what I'm basically saying is that this thing here, this is our antiderivative. This is our f of x. Now, why is that our f of x? It's our f of x because, by definition, if you differentiate the antiderivative, so if you differentiate your uppercase f of x, so differentiate with respect to x, 4 over 3 x to the power of 3, and I'll put the plus c in as well. What would we get? Well, the 3 would multiply to the 4 over 3 to give you 4. You reduce the power by 1, which goes down to a power of 2. When you differentiate a constant, you get 0. So we've ended up with 4x squared, which is what we started with. So that shows that this is the antiderivative of that. So one of the big challenges notation-wise, because remember we're talking mainly about notation in this class, is that when you're doing differential calculus, so let's say that we started off with this function here. So f of x equals 3x to the power of 4. So we take the derivative using the power rule, and we notate that derivative as f prime of x, okay? So multiplied by the power gives you a 12x to the power of 3. But we've used this notation, f prime of x, to notate the fact that we've taken the derivative. We've already used the power rule at that point. But it's different in integration. In integration, when you see the symbol, that's not telling you that you've taken the integral already. It's telling you that you've still got to do integration. So this symbol represents the integral, but we've not actually done integration at this point. I've done integration between here and here. I've actually used what we're going to define in the next class as the power rule for integration to go from the 4x squared to this 4 over 3x cubed plus c. So that's where the operation exists in here, and that operation was initiated by the fact that that symbol was there. That symbol tells me to integrate. It's saying integrate the function 4x squared and do it with respect to x, whereas the f prime of x notation from differential calculus, that is not telling you to differentiate, it's telling you you've already differentiated. So there's a slight issue there, a slight disharmony, I guess, between the two uses of the notation, which often causes issues for students. So be attentive to that. I mean, you're going to learn this stuff very quickly by practice, but these notational issues are not easy to sort out at first. Okay, let me just show you this other example. So slightly more complicated thing, but again, you will learn to integrate this by the power rule. So we're looking basically for our f of x, okay? We're looking for our antiderivative of this function, and you will learn again the technique for doing this, but basically this one becomes minus 2 over 3 x. Let me just think about this for a moment. Yeah, minus 2 over 3x to the minus 1 power, and then you could put again you will learn to put your plus c on the end. And again, why is that? Just let's sort of self-check it. It's like that because if you take the derivative with respect to x of this thing that I'm saying is the antiderivative, so minus 2 over 3 x to the minus 1 plus c, what do we get? Well, we can apply the power rule to that. The power rule says multiply by the power, so the minus 1 times is to the minus 2 over 3 to give you positive 2 over 3. You reduce the power by 1, so it goes down to an x to the minus 2. The plus c, again, is just a constant, a number, so when you differentiate it, it goes to 0, disappears, and you're left with this here, which is what we started with. So in other words, this here is the antiderivative, or this here is the antiderivative, or the integral of this function here. So just notice the way we've notated it again. This is saying integrate the function 2 over 3x to the minus 2, do it with respect to x. The with respect to x is a no-brainer here because it's the only variable that's in the function. In fact, most of the functions, I think all of the functions you're going to see in this course are single variable functions. So this is just going to be a notational thing that you're going to have to write on every time. It becomes a bit of a habit, I suppose. In the same way they put in the plus c, will become a bit of a habit. But this is telling you to integrate that function with respect to x to find, in other words, the antiderivative, which is that function there. So these first 3 classes, these first 3 videos, if you watched all 3, it's just really setting up integral calculus. So we've defined the antiderivative, and now we've started to look at the notation that we use to connect antiderivatives with this sort of original function. But the missing link for you at the moment is this part in here. This here is the technique. In this case, it was the power rule. It could be different rules. It depends on the original function. If it's a composite function, you'll have to use the chain rule, or the reverse chain rule, we call it in integration. So a bunch of techniques to learn. Let's start now filling in the gaps, filling in this technique by learning all of these processes. And we're going to start in the next class with the power rule. So hopefully this sort of framing in these first 3 classes has set things up nicely, and now you're ready to start learning the techniques. So when you're ready, just scoot on into the next class where we're going to learn the power rule for integration.